Well, hey, this is a little introduction to what you're about to face this semester with multivariable calculus. And to bring us to the multivariable calculus world, let's first start with a single variable reminder. Now, the reason we call it single variable is this. Here's just an example I pulled. The price per gallon is a function of the single variable quantity of gasoline in millions of gallons. So this is a typical supply and demand curve. Maybe you've heard of it, supply and demand. When the quantity of gas, when the demand or the amount of gas is high, the price is low, and when the quantity is low but demand is high, the price is high. And it's just an example of how economics works. But what I want you to focus on, it's not a supply and demand economics course video. It's just a reminder of you have traditionally in your mathematics courses been studying situations where a single quantity, an output quantity, is a function of a single quantity, in this case, quantity of gasoline. And what we would say is the price per gallon is a function of the quantity. So y equals f of x. Traditionally, y equals f of x. That y-axis, that vertical axis, is a function of the single variable x-axis, the horizontal axis. But now we're going to move into a world where we can think about multivariable functions. And I want to convince you just immediately here that this is not uncommon. Think about this situation. Auto insurance. If you've ever had to think about auto insurance in your life, you would quickly realize that this is a multivariable function. The premium that you pay for your auto insurance is a function of, and I've left this blank because I want you to just think for a minute. The premium you pay for your car insurance is a function of what other quantities, plural, multivariable, a function of several variables. Think with me on this, okay? Here's what I'm thinking. Your age. One input that determines the auto insurance premium is the age of the person to be insured. A 16-year-old will pay more for auto insurance than a 36-year-old, for example. Because of the statistics, because of a field of mathematics called actuarial science, they look at the data and it's just a higher risk. Statistically speaking, it's a higher risk to insure a 16-year-old than a 36-year-old. What else are you thinking besides age? Are you thinking what I'm thinking? The value of the vehicle. The greater the value of the vehicle, the more the insurance. If you drive a 2002 Kia Spectra, I think I just mentioned my car, that has a salvage title on it, and it's worth nothing, you pay very little insurance on this car. But if you've got a 2022, some fancy vehicle, you're going to pay more insurance. Because why? And if something were to happen, the car is stolen, the car is damaged, the car is destroyed, the insurance company is going to have to pay more to replace, fix, whatever that car, so you pay more in a premium. What else? What else are you thinking? I'm thinking R. Now, what could R stand for? Well, to be honest, I don't remember what I had when I put R here, but another thing that auto insurance premiums depend on is the gender of the person applying for this auto insurance. Again, statistically speaking, let's go back to age. Young male drivers are a higher risk to insure than older female drivers, and so that goes into the formula that actuaries use to determine the premium that you will pay for your auto insurance. The point is this. Auto insurance premium is a function of many variables, not just one. And I put ... here because it goes on and on and on. There's many, many, many more that these companies use to determine the auto insurance premium. But what does that mean for us now? Instead of just a single variable function, that is, there's one output quantity as a function of a single input quantity, we now have a situation that looks like this. We have a output quantity that's a function of, let's say, 2 input. Let's just start with 2 input quantities. And traditionally speaking, instead of x, y, and z, I had messed that up a little bit. Instead of x, y, and z, z is a function of x and y. Now notice, all of these are at right angles. There's this, the way we make Cartesian coordinate systems is the axes are at right angles to one another. And so there's a right angle here, there's a right angle here, there's a right angle here. This is the origin, and I'm just showing you the positive, positive, positive portion of a three-dimensional graph. But there's all kinds of, there's 8 octants now. Remember in two-dimensional, in a single variable function situation, you had 4 quadrants. Well, now you have 8 octants. And what we say is, instead of y is a function of x, we say z is a function of x and y in a three-dimensional, 2-variable situation. The 2 variables are the 2 input quantities, and then the third dimension is the output. So this is what you're going to be looking at a lot in our Calculus 3 class. Now, just as an example, again, I don't mean for this to be some big, deep think about the context, but just so you have some awareness that these things happen. This is a regression model, and I believe came from Harvard University, where they predicted the grade average, PGA, the predicted grade average of incoming freshmen. And the model is based on your high school GPA on a 4-point scale, your SAT verbal score, and your SAT math score. So what we would say here is the PGA, the predicted grade average, is a function of 1, 2, 3 variables. So it's a 3-variable function. It would be graphed, if you could do it, in 4 dimensions. Not that we can physically imagine or create 4 dimensions, because we live in a 3-dimensional world. That's what this would be. The 4th dimension in this case, not in some weird mystical way, it's just the PGA is the output quantity that depends on 3 input quantities. And then based on this model, we could do some explorations here, like, is it possible to have a predicted average of 4.0? Could you have a 4.0 come out of this formula? Well, imagine a perfect 4.0 high school GPA. Imagine a perfect 600 on the SAT, and I'm sorry, 800 on the SAT verbal and 800 on the SAT math. Now, you'd have to know that there's 1600 possible. A perfect SAT score is 1600, so 800 and 800. Well, if you tried 4 here and 800 here and 800 here and crunch the numbers, you would see what the outputted PGA is. Or is it possible to have a predicted average that is negative? Like, could you input things for these 3 quantities such that the output is negative? You could play with that and see which variable is most important and why. And you might look at this weight 0.708 times the high school GPA has a pretty heavy coefficient on it. So maybe it has the most important weight on the PGA. Anyway, the point is not to examine this really closely at this moment. The point is just to see, I want to convince you that multivariable functions are probably more prevalent in the world than just single variable functions. Here's another. The heat index. For us living in the Phoenix area, the heat index. The apparent temperature, how hot it feels like outside, is a function of 2 things, the air temperature and the relative humidity. You may have heard in the Phoenix area, the Valley of the Sun, we say it's a dry heat. And what we mean by that is we have low humidities. Like, we might be in this range. So if we have low humidity and the air temperature is even 110 or 105, notice that it feels like less than that. Now compare that to if you're from a high humidity location like the Midwest or the South. They have maybe not as high temperatures, but even if they're in the 90s in the summer with that high humidity, it can feel like a lot warmer. Look at this one, 136 it looks like. So, but the point again is the apparent temperature is like the Z value is a function of 2 input quantities, the relative humidity and the air temperature. We have multivariable functions everywhere. So how do we mathematically imagine them? And I want to encourage you starting right now. Here's your first video of the course. I want you to jump on to GeoGebra, geogebra.org, and start that calculator. And the reason we're using this instead of Desmos is because GeoGebra has a 3D calculator. So just as a quick play, right now you should be opening a GeoGebra and play along with me here. In GeoGebra, we can do things like this. Let me jump back. Suppose you wanted to just plot the point, 3, -4, 9. 3, -4, 9. You just type it in. Ordered triple. Remember, in 2D, single variables, we would have had an ordered pair, x, comma, y. We now have an ordered triple, x, comma, y, comma, z. So 3, comma, -4, comma, 9. Now, I specifically picked 9 here so you could see it's off the screen, but if you put your cursor on any one of the axes, in this case the z-axis, and hold down shift, you see that? Now if you click and drag, you can scale just on that axis. And you can do the same on any one of the, oops, I'm not hitting shift. You can scale that on any one of the axes, one at a time. But there it is. And if you click and drag, you can look at that point hovering there at 3, -4, 9. Now, one little trick I've learned is when you're working with this, pretty soon you go, oh wait, where did it all go? I can't remember which axis is which. We'll come here to the gear and go to settings. And I like to just label, I'm on the x-axis, let's label the x-axis x, let's label the y-axis y, and if you were in some context that was using variable names that were meaningful, you could have labeled them appropriately. But now you can kind of keep track of which is which, especially if you do it properly. It looks like I labeled the y-axis alpha. Let me try that again. There we go. Now, the traditional version of this is positive x-axis coming out at you, positive y-axis to the right, positive z-axis up. So here it is, 3, -4, 9 gives us that point. All right, cool. What else can we do with this thing? X equals -3. Let's use GeoGebra to imagine x equals -3. Now, if x equals -3, x is the red axis now. If x is -3, there it is as a point. But if we move over here, x is still -3. If we move over here, x is still -3. If I move straight up or straight down, x is still -3. So what would x equals -3 look like on this graph? There it is. It's a vertical plane where x is always -3, but y can take on any value, z can take on any value, but x is always -3. So we get this, we just call it a wall back here at x equals -3. Well, what about y equals 5 is what I had next. What about y equals 5? You should be able to imagine that now. Before you even type it in or watch me type it in, y equals 5, and y is always 5. So if y is always 5, we can move in this direction and y is still 5. We can move up and down and y is still 5. So y equals 5 produces another vertical plane, another wall over here where y equals 5. And then finally I had z equals what? -7. So z equals -7. I hope you can imagine now what this one looks like. Z is always -7. Now we might need to do some scaling on this one to see it. There it is. So z equals -7 is like a floor. Or maybe if z was equal to positive something, you might call it a ceiling in this room. So imagine like a wall, and a floor. Z equals -7. Now, let me turn those off, because what if now we have not just these nice constants, but we have, what do I have here? X plus y equals -6. What would it look like if x plus y were always equal to -6. Aha, there it is. X plus y equals -6. Now watch this. If we move this into the traditional xy plane, do you see the line? This is the line y equals -6 minus x, essentially. You can see it on a couple of points here. When x is -6 and y is 0. When x is -6 and y is 0, we of course go through that point on the x-axis. Or when y is -6, that's down here. When y is -6, I guess I need to scale that a little bit better. When y is -6 and x is 0, we also have an intercept. And then we have all the points in between. And we have another wall, another vertical plane, but it slices through, in the two-dimensional space, it slices through that line, y equals -6 minus x, or x plus y equals -6. So getting intercepts is kind of a nice strategy. You can pretty easily see, oh, if x is -6 plus 0, -6, 0 would be a point in the xy plane. Or 0 plus -6, and y is -6 would be another intercept. But then z can take on any value it likes, and we're still such that x plus y equals -6. Another convenient point would be -3, -3. Can you see it? -3, -3. -3 plus -3 is also -6. And then all the points in between creates this plane. So let's just do one more. Y minus x equals 8. Now before you type it in, or before you watch me type it in, will you try to make a guess of what it would look like? Y minus x equals 8. See if this one makes some sense. Let's look at it in the more typical XY plane. Hey, by the way, if you click the 3 dots and go to settings, you can change the color on these things. I'll make it a little darker. Let's make it black, so hopefully you can see it well. See if this makes sense. The y-axis is here in green, the x-axis is here in red. So when x is 0 and y is 8, yeah? Or when x is -8, you can't quite see it, but when x is -8 and y is 0, 0 minus -8 would be 8. And then all the points in between where y minus x equals 8, and then in the z direction, you've got this wall again, a vertical plane that kind of slants through the xy plane accordingly. Now one last thing, in terms of language and vocabulary, when I was showing you this, we're looking at the xy plane, or the yx plane, like we typically have done in your math career. But we can also look at, say, this way. This would be the zy plane. When we look at just down the x-axis, we're seeing z and we're seeing y. That's the zy plane. And then, of course, if you're looking down the y-axis, we're now looking at the zx plane. So we can look at these things from those different perspectives, xy, zx, zy, and we can see what things look like. Welcome to the world of multivariable functions. I hope that gives you a good introduction. Continue on in these Google slides and learn even more.